Welcome back, guys. This is going to be the 9.1 instructional video, part 2. Okay? And in 9.1, the first one, we introduced a lot of theory. But really what it boils down to is we're learning about this topic called confidence intervals. And what are confidence intervals? Well, they're intervals of that we are a certain degree of confidence is placed in that we're going to use to estimate population parameters. What we introed and what we're going to talk about here is specifically we're going to focus on the population mean. And unfortunately, unlike the population standard deviation and sample standard deviation, given certain specifications about the population being somewhat normal in a sample size greater than 30, according to our first definition, the population standard deviation and sample standard deviation are equal. Not the same case with the population mean and sample mean. So how do we predict the population mean? Since the two aren't the same, remember that difference being called the error of estimate, how are we going to use the sample mean to predict the population mean? And we're going to do it through confidence intervals. If we don't know the exact value, at least we can come up with a range of values that the population mean is between. And the sample mean is going to play a role in that. And the concepts or the theory behind it really go back to chapter 8. If you remember in chapter 8, we talked about the population of all the trout in the pond. Then we had 100 samples that for each sample we found the mean for. So we had 100 sample means and we made a distribution out of those. A distribution of sample means or a distribution of any statistic is called a sampling distribution. And through two theorems, theorem 1 and theorem 2, we learned that if either the population being normal or the sample size being bigger than 30 meant that our distribution of sample means was normal. And it had some important consequences. But what we're going to do is we're going to tie in that idea to making confidence intervals. Because when we use a normal distribution, if we look at, well, we don't know population data, if we look at a distribution of sample means, if the sample size is large enough, that distribution of sample means will be normal. And so what we can do is, since it's normal, we can look at the area under that curve and have valid probabilities that while we may not know the population mean, that if we look at the distribution of sample means, and that distribution of sample means is normal, the population mean will equal the mean of the sample means. And so we can use that normal distribution on that distribution of sample means to come up with an interval that we can say with a degree of confidence that the population mean is between a certain value and a certain value. That's kind of the idea behind confidence intervals. And that may be very confusing to some of you. It's a hard concept, folks. But here's what it's going to boil down to. We're going to use our sample mean and data to come up with an interval of values that we are a certain degree of confidence in. We experimented with this in the first video when we looked at critical values. What did we do with critical values? Well, we talked about that concept that we're going to use the normal curve because the area under the normal curve is equal to probabilities to determine our level of confidence. If I want to be 90% confident in a set of numbers, I'm going to look at the normal curve and I'm going to find the set of numbers such that 90% of the data is in between the two. Again, because the normal curve the area under the normal curve is equal to probabilities. If I want to be 90% confident in something, find the two values such that 90% of the data is between those two values under the normal curve. And so we did that with the standard normal curve because we know the mean and the standard deviation of the standard normal curve. We were able to do that. And we did a couple examples with inverse norm or with 95%, 99%. We found the two data values such that 99% of the data under the normal curve was between the two and 95% of the data of under the normal curve was equal to. And consequently, we had values that we knew that there was a 99% chance that a given variable z on the standard normal curve would fall between those two values. Okay, it's pretty confusing. Where are we going with this? Well, we're not going to work with the standard normal curve anymore. Instead, we are going to put it all together. And it really comes down to the following formula. Since most of the time we aren't working with the standard normal curve, we have to find a way to calculate the two values that give us our confidence level that we are looking for. And here is our formula for the confidence interval. C is equal to P of x bar minus E is less than mu is less than x bar plus E. This is our formula for confidence intervals. And here is how we can read this. C stands for confidence. This is going to be 90%, 95%, 99%. However confident we are in the range. That range of values is this. Mu, remember, is the population mean. X bar is the sample mean. And this big E is going to be error. And again, this should make sense, right? The whole idea of a confidence interval is I am some level of confidence that my population mean will be between blank value and blank value. And what participates in finding those values is using this sample mean along with some sort of error, okay? We could think of it as the difference between the population mean and the sample mean. We're trying to find that difference. If you want to know where this formula comes from, talk to me outside of class and I'll happily sit down with you where this is all going to come from. It's fairly complicated. So I think for our level of studying of statistics, we don't really need to know the ins and outs of how this formula was developed. But if you would like to and you're interested in that and to know where the formula came from, sit down with me sometime. So this is our formula for confidence levels. The question, obviously, that's popping in your brain is, how do we find E? How do we find the error? Well, error is going to be Z of C times sigma over the square root of our sample size. Now, if we don't know, we've talked a lot about this, if we wouldn't know a population parameter like sigma, if we don't know our population standard deviation, definition 1 helps us. If our sample size is large enough, we'll just substitute S in for sigma. Again, as long as we know the population somewhat normally shaped and that the sample size is greater than or equal to 30. Okay, so this is our formula here. Again, what it says is we are 95, 90, 99, whatever confident level that our population mean is between X bar minus some level of error. And how are we going to calculate that error? We are going to take our critical value that we've talked about above, right? The critical values are the numbers on the standard normal curve that we know so much data is between. And we're going to multiply it by our population standard deviation and divide that by the square root of our sample size. Okay? This will kind of help take our data, or looking at the standard normal curve and whatever data set we're working with, apply our conclusions on the standard normal curve that 90% of our data is between blank number and blank number on the standard normal curve, and apply it to our specific data set. So to recap, here's what you need to know. Your formula for a confidence interval is going to be X bar minus the population mean, X bar minus E is less than your population mean, is less than X bar plus E. We're using the sample mean to predict the population mean. Specifically, we're coming up with an interval that we know the population is between with some degree of confidence, 90%, 95%, 99%, etc. X bar is going to be your sample mean. And E, our error, is equal to our critical value times our population standard deviation divided by the square root of our sample size. Remember, if we know sigma, we will use it, but if not, we can substitute S in instead. That's back to our first definition we learned today. C is going to be the confidence level that we have that the population mean is between X bar minus E and X bar plus E. Remember, there are two parts to a confidence interval. What's the interval and how confident you are in it? C is going to be that level of confidence. Z of C is going to be the critical value. Remember, if we look at the standard normal curve, what's really nice is the area under the standard normal curve is equivalent to probability. So if we want to be 90% confident, we want there to be a 90% chance that the mean's between two values. We can start by looking at the standard normal curve and going, okay, on the standard normal curve, what are two values such that 90% of the data falls between them? Those are the critical values, and we use them in our calculation of our interval. And then finally, N equals our sample size. So with all of that being said, all of that being gone through, how do we actually solve a problem? What's this going to look like? Well, Julia enjoys jogging and has done so for several years. During this time period, her physical fitness has been in great condition. Typically, she jogs 2 miles a day. To monitor her fitness, she has collected 90 sample times of her 2-mile runs. For these 90 samples, the mean was X bar equals 15.6 minutes, and standard deviation was S equals 1.8. Let mu be the mean jogging time for all the runs she has done over the past several years. Find an interval such that Julia can be 90% confident or 95% confident her overall average run time is between the two values. So we have our friend Julia, and she's been tracking her jogging more recently. She's collected specifically 90 sample times. Okay, so her sample size, we would say, is 90. And in those 90 samples, she got a sample mean of 15.6 minutes with a sample standard deviation of 1.8. So she ran, in the 90 runs she calculated, she had an average runtime for her 2 miles was 15.6 minutes with a standard deviation of 1.8. And again, this is just one sample, right? The sample size is 90, but we could imagine maybe if she did another 90 days, her X bar might be a little different. And if we had, let's say, 10, 20, 30, 100 different sets of 90 days, all those X bars would create a normal distribution. Okay, so we're trying to find an interval such that Julia can be 95% confident her average runtime is between the two values. Okay, we don't know her average runtime over the span of the 2 years. She doesn't track every single run she does, but she would like to know what it is. And we want to be 95% in whatever that interval we come up with. So, how are we going to solve the problem? Well, we have identified our sample size, our sample mean, and our sample standard deviation. And we know our formula for confidence intervals is X bar minus the error is less than the population mean is less than X bar plus the error. Okay, that's going to create our interval. Well, we know our formula for error is taking our critical value times our standard deviation divided by the square root of the sample size. Well, what's our critical value? Well, we want to be 95% confident her overall average runtime is between the two values. So, how do we find that critical value? On the standard normal curve, we want 95% of our data to fall between two values on the standard normal curve, such that if we picked a random variable z, there's a 95% chance it would be between these two numbers. Well, that means that 5% of our data is broken between the two tails. So 2.5% will go to each tail. Right? If 95% is the shaded region, then 5% is the non-shaded region, and that's on either side, so 2.5% on each side. Which means if we set up inverse norm, we find that our critical value on the standard normal curve is 1.96. Negative 1.96. Again, what's our area left of our critical value for our right boundary? Well, that's going to be 0.975 is going to be that area left of that critical value, because 95 and 2.5 had to be 97.5%. Turn that into a decimal. And when we run our inverse norm, we find that we get 1.96. So we do this because this is our critical value. This is the range that on the standard normal curve, 95% of the data falls between it. Meaning we're 95% confident that a variable, random variable z on that normal curve will be between these two numbers. But we're not working with the standard normal curve here. We're working with Julia's data. So we take that critical value times the standard deviation. Now we don't know the population standard deviation, but we can use the sample standard deviation in place of it. And we divide by the square root of the sample size. And I find that my error is 0.37, which, let me erase here. If the error is 0.37, then to find the confidence interval, I subtract that value from my mean, which was 15.6, minus 0.37, plus 0.37, and I end up with an interval of 15.23 to 15, or is less than the mean, is less than 15.97. Which means that our friend Julia, given that sample data, given that sample of 90 run times with a sample mean of 15.6, we can use that to predict that her average runtime over the course of the last 2 years is between 15.23 minutes and 15.97 minutes. And we can say this with a 95% level of confidence. This is the confidence interval process. Okay, let's try another example. Again, if you're confused at this point, please make sure you're starring the parts of your notes that are confused. That way I can go back and help you. Email me any questions you have. I would love to help you out. Let's say Julie has a friend named Walter, and Walter usually meets Julia at the track, and he prefers to jog for 3 miles. Well, Julia kept her record. He also kept one for his time to jog 3 miles. For his 90 times, the mean was 22.5 minutes, and the standard deviation was 2.4 minutes. Let mu be the mean jogging time for the entire distribution of Walter's 3-mile running times over the past several years. Find a 99% confidence interval for mu. So similar to his friend Julia, Walter wants to know, looking at the data of his 90 runs, his sample of 90 runs, Walter would like to know, what is my average run time over the course of the last 3 years in general? And while we can't give Walter an exact amount, we can give Walter a range of numbers based on his data with a certain level of confidence of what his average run time may be. Okay? So we need to create this confidence interval for Walter. Well, what are we going to do? Well, we know our confidence interval formula. X minus E is less than mu, is less than, or X bar minus E is less than mu, is less than X bar plus E. Remember that air is made up of our critical value times our standard deviation divided by the square root of the sample size. The critical value becomes important because this is where the confidence level plays in. We're going to look at the standard normal curve and find the two values, our critical values, such that however confident we want to be, what those values are, that amount of data lies between. Because the amount of data under the standard normal curve is equal to probability. So if we want to be 99% confident for our friend Walter, we need to find the two values such that 99% of the data on the standard normal curve lies between those two values. Well, if 99% of the data is going to be between those two values, then 1% is left for the non-shaded region. That 1% can be divided into the two tails. So we have 0.5% on each tail. So to find our critical values, we use our inverse norm function because we're working with the standard normal curve, and we want to find data values given a probability. Well, the amount of area left of negative z of c is 0.005, since 0.5% is to the left of that data value. amount of area to the right of our Z of C, our positive critical value, would be 99.5% or 0.995. When we calculate it, we find that on the standard normal curve, that 99% of the data falls between negative 2.58 and 2.58 on our standard normal curve. So 2.58 will act as our critical value. But we're not working with the standard normal curve. We're working with Walter's data. So we're going to multiply the standard deviation of Walter's data times that critical value. Standard deviation for Walter's data was 2.4. And we're going to divide it by the square root of his sample size, which was 90 runs. And when we do this, we get 0.65. Again, pause the video if you're still catching up, because I got to erase. So if the error in Walter's runtime, the error is 0.65, we can subtract that from our mean. And what we end up with, Walter's mean runtime was 22.5 minutes. So we subtract that from the mean, our sample mean, and we add our error to our sample mean. And we find that we can say with 99% confidence that Walter's average running time over the past couple years is going to be between 21.58 minutes and 23.15 minutes. We are 99% confident that Walter's 3-mile running times over the past several years, given this sample data, will fall between 21.58 minutes and 23.15 minutes. Guys, I appreciate you watching. I know it's somewhat confusing, but I think we're going to get pretty good at this quick. Have a great day.